Hello and welcome to another episode of Deep Dive into Applied Science. Today we are talking with someone from the Environmental Campus Birkenfeld, and our guest can introduce himself.
Thank you, Martin. Hello together. My name is Joachim Brinkmann. I'm a PhD researcher at the Environmental Campus of Birkenfeld. And, well, can I directly start with my topic, or?
If you want to, yes.
Well, my research topic is resource efficiency in additive manufacturing.
Maybe you can also describe your project a bit broader, but still in one sentence, if possible.
My research is about optimizing resource and energy efficiency in additive manufacturing with energy model analyzers.
What exactly is additive manufacturing?
Okay, the easiest word in my title. Thank you for this. Additive manufacturing is also called 3D printing. So it's like the 3D printers we use in our households. Usually the 3D printers use a plastic. The process is called fuse deposition modeling. So the plastic is melted into a layer, so a sheet, and, well, a model is built up. The process I use is called PBF-LBM. It stands for powder bed fusion, or PBF, powder bed fusion, LBM, so laser beam, and the M is for metal. So my work is with metal powder, and the process, well, today is called PBF-LBM, and it comes from SLM. It's the name for selective laser melting. So I use a metal powder. It's in a powder bed, and the laser beam melts the powder to one layer. After one layer, a new sheet of powder is spread to the powder bed, and the laser beam starts again to melt down the hatches.
Before we dive deeper into some other technical questions, one question before. Why exactly did you choose that topic and not something different?
Well, from my basic studies, well, I'm a mechanical engineering and I made a master's degrees in environmental and energy technology. I have a splitted specialty, one in engineering, one in energy technology, and we created research project about, well, two specialties, the resource efficiency and additive manufacturing. So that's why I chose this.
You also talked about the resource efficiency. So what exactly do I understand under this term? How do you find out which process needs which amount of energy?
Energy is a resource. So when we talk about different resources, I do not only measure the energy amount, I also measure the amount of powder that is used. So there's some waste powder. For melting processes, we need inerting gases like nitrogen or argon. So there's a consumption of these technical gases. There's pressurized air. There are some usabilities in the machine. So this is what I understand under resources, and as well as the energy consumption.
How do you measure the energy consumption?
Okay, that's kind of easy. I install an energy meter. So it's like a data logger. So on the one side, it measures the voltage and the ampere to calculate the power that we use. And on the other side, it data logs the values within a small amount of time. So it's like an energy logger in your household. So you have one, and this smart meter measures the amount of energy every 15 minutes. But I use a smaller time spread. I use data in the range of 10 milliseconds to 1 second, so that I have a deeper look into the energy data.
So after you gathered all that data, what exactly do you do with it?
The analysis of these data is one main part of my research, because, as I mentioned, I data log the data in the amount of 1 second. So a 3D print or a process to build up, let's say, 100 tensile test specimen needs an amount of 40 hours. Yes, exactly.
Quite a long time, yeah.
Quite a lot of time. So there's the voltage, there's the power of 3 phases, there's the consumption of pressurized air, of the inert gases, and so on. So I have data points of more than over 300,000 points. So I have to program analyzes programs in Python to analyze this. So in the end, I have a consumption line, so energy diagram, how much power I need at which point of the process. The interesting thing is then that I can split this information into different phases and systems. So that's the point where we dive deep into energy modeling. That's what I do. I use these data, analyze them, and build up an energy model, split it into different phases and systems to predict the energy consumption of future processes.
So with said data, you basically can compare how much energy different systems use. Is that right?
Yes, it is. So with these energy models, we can more or less directly compare how high the energy amount or resource amount in different systems is. The problem is every system is specific. So some systems need nitrogen as inert gas. Other systems don't have pressurized gas. So the basic parameters are different. So you need one energy model for every specific machine.
So in other words, companies can also use this data to see which model or which system is the most efficient?
Yes or no? Again,
the best answer.
One idea of an energy model is exactly this. Which is the most efficient system I can buy for my process? Yes, for this, easy models or over-the-thumb models like the SEC model is called Specific Energy Consumption Model is a good idea. So you get an amount of how much kilowatt hours you need to melt 1 kilogram of metal. But you have to consider that there is a difference between aluminium powder and stainless steel powder. So also this easy model like the SEC is specific for every machine and every metal powder or even plastic powder.
Mm-hmm. So I can imagine that you use different amounts of energy to melt 1 kilogram of steel, or I don't know, 1 kilogram of plastic. It's probably very different. So I'm not quite sure in which industries you have to melt 1 kilogram of steel. So which industries exactly can profit from your work or can, well, take a benefit out of it?
Well, in different industries, we need some lightweight products, for example. We want to optimize the weight of products or of models. So additive manufacturing has more degrees of freedom, like lightweight builds, holes, lattice structures, so that it's like when you have a full cup of metal powder from a CNC machine, it is a full body cup, and with a lattice structure, there would be a small construction structure in lattice structure called. So these lattice structures make the cup much more lighter than a full body cup. So other degrees of freedom are integrating of functions, for example, or initialize topology optimization. So when I stand on this cup, there is a specific force to this cup. The topology optimization calculates this force and changes the thickness of the walls along the lines of the force. These models with the lattice structure, topology optimization, functions inside, like cooling channels inside of the cup, They can only produce by additive manufacturing, not by conventional manufacturing. So this is what the industry can use. So my empirical energy model is more on the construction side. So with my model, a constructor could check how high the amount of energy is used for his constructed model, for example, or if it changes the direction of the process, if the energy consumption is also changed.
For this whole project, you also collaborate with the Carl Zeiss Foundation. Please correct me if I'm wrong. How does this collaboration look like?
Well, since this year, there is the new Carl Zeiss project that is called Kraft. Kraft stands for circular economy and resource efficiency through additive manufacturing.
That's a complicated title.
It is, but it's nearly my research topic. So that's why I collaborate with this. It's a really interesting collaborative project with two more institutions. One is the University of Applied Science Aalen, and the other one is the KIT, Karlsruhe Institute of Technology.
And when exactly did you start your whole PhD?
Well, the start of my PhD journey was the first start of the first research project I got. This project was called RERAP, Resource Efficiency in Rapid Prototyping, with the aim of the comparison of conventional manufacturing to additive manufacturing and the energy analysis. So this was the start of my research and also of my PhD. Yeah.
And a difficult question for some people. When do you plan on finishing it?
Next year.
Next year. Oh,
yes.
That's very specific, yeah? And if you look back at your whole journey, what has been the biggest challenge so far?
RERAP started in the year 2019. We all know there's one black time period in the beginning of 2020.
A black hole. Yeah, that sucks all the energy out
today,
of us.
Whatever talk about this period, what we did, what we thought, and so on. Well, this was basically the first challenge in this research project. One challenge was caused by the pandemic situation. Some of the partners had economical problems. So they said, sorry, but we cannot do research now. We have to concentrate on our business. And the other one was that we could not meet. We could not meet with other researchers and so on. This was, one of the bigger challenges. Yeah, the biggest, I think. Yeah.
So overall, it sounds like a lot of industries, at least from my point of view, can profit from additive manufacturing. If people are interested in your work, in your person, in any information whatsoever, how can they contact you? How can they reach out to you?
Just search for Joachim Brinkmann at the homepage of Environmental Campus of Birkenfeld. It would be easy. Or everything that is tagged with CZS, Carl Zeiss Stiftung, or Kraft project, anything else. So, I now work with or in this project, so there is a good possibility to contact me. Yes.
Perfect. So your contact details are on the website of Trier University of Applied Sciences. So thank you very much for coming on Deep Dive, for presenting your research, your topic, and so on. I wish you all the best for the next year. I hope you finish the project. And thank you very much for watching, maybe for listening. And we will see and hear each other in the next episode of Deep Dive into Applied Science.